So I will do this presentation in name of representing an association that we're running, in which we're trying to promote science and also outreach in science to show people what it's CERN about and what the things that are really going to the society from what we are learning in CERN, for example. And what I'm going to present is the title. So, searching the Higgs Boson at CERN and how it impacted the world of communications. And there I highlight the three words that for me are the most important for this presentation. So I will explain a little bit what's the Higgs Boson and how we try to search this kind of particle. It will be a brief presentation so that we can just warm up and set all the things for the following. So the following is CERN. So what's this laboratory, what is said, and how does it work. And finally, this could be the most important part of the presentation. I will try to link what we do there at CERN or developments related with communication in the past and what can we expect in the future about communication that has been, for something that has been discovered or studied in such a laboratory. So let's start with physics, so we can understand and see the motivation of such a big experiment. We'll talk about CERN. There I will tell you we're 10,000 people working in a high-budget project in which we're trying to learn a little bit more about nature. So you can understand what we're trying to do, the aim of everything. I put this image of Einstein because it represents the final goal of a fundamental physicist, and it's finding a final theory that can describe anything in terms of fundamental building blocks of nature, we call particles, and the fundamental laws of nature, so interactions. So this was the dream of Einstein, that was his work in the final years in which he was working with these kind of theories. But this story can go back to the very first civilizations, like the Greek, where they started this reasoning of trying to find the fundamental laws of nature and the way the universe was built. And this Einstein dream of finding a final description of nature should be based on these 3 points that are somehow philosophical interesting for a physicist. Trying to find something simple, because we think nature should be simple, something beautiful, because in the end this is how we think the world should be based on, and finally universal, in the sense that it should be working in any case. And to do so, I'm showing here all the way from the previous civilization, you see here before Christ, to the present situation of physics. So here I represent what we have been working since we start in the beginning of the history 3,000 years ago to what we have today, after all this we have learned from the past. And this I would like to give you the idea of how we're trying to merge different phenomena and different knowledge that in the beginning appears to be something not related within each other, but in the end there is something common. And this is what we're trying to do. We're trying to explain everything in a common basis, so that everything can be understood with simple formulas, simple equations. So this is a story, a simplified story of what we have been doing in science since the Greek civilization, and we have here the different areas and how they have been merging towards a final model that is what we call right now the standard model. This standard model is successful in the way the Einstein dream was shown before, in the sense that it's merging all the knowledge from the past. Here examples like electricity and magnetism into electromagnetism, and all the knowledge converging towards a final model. This standard model will respond to all these requirements from this physicist philosophy of having something simple, universal, and beautiful. And here the same with the particles. So we have the 4 elements from the ancient civilizations: earth, air, water, and fire, and how it has been developing with the history of humankind. So at the table of Mendeleev, that's the atoms. Finally, we have this table, that is table of standard model, that we think is the final description of the building blocks of nature. So the standard model responds to what I said before, this goal of finding something that will describe everything. So right now it's describing the different interactions and the different particles in the universe, and it's doing, as I said, not only qualitatively but also quantitative. So we have a formula, an equation that is able to respond to any phenomena, that is able to describe any phenomena based on these interactions and this particle. And this is a simple equation, beautiful equation that can work in any, it can work in any environment. So any phenomena you can imagine, related with light, with magnetism, whatever you want, you go to this formula, you plug the input, and you get where you want. Right, I bet you think this is not simple, right? That's one of the problems. It doesn't look simple, but it does. This is an expanded formula that I show here for short. This will be the formula in the short version, but in the end it's exactly the same. It represents the same as before. Was the previous one was just to let you get you frightened, like, what's that? So this is the formula, and you have to understand from this formula, this equation, there you derive and you get how the particles interact. From this formula, what you have to understand is the power of this formula and the importance of this formula. Anything you go to a library and you get a book on physics, engineer, it doesn't matter which book you take, you can explain whatever is there, starting here. So anything related with applied physics, physics of materials, engineer, whatever you want can be taken to be understood based on these terms here. And so that you can understand the importance of what we're doing now and the importance of this formula with the first element there, the 2F that you see there, you can extract the Maxwell equations. So this is really interesting and really powerful. Just having all the physics that we have from electricity and magnetism concentrated just in this term. And can you guess what this thing is here is? Any idea? For those that have been have seen kind of this presentation before, can you imagine what this thing is?
It's something about relativity, I don't know.
No, Higgs boson. It's the Higgs boson. So that's why the Higgs boson is so important. It's in the heart of the model. Within this Higgs boson, the model wouldn't be consistent. So all the model that we have been created through the history depends on this particle. And that's why this particle is so important. Because it's a confirmation that this model is somehow right. And to give you an idea of how simple it is, I show here how it can fit in a map, how it can fit in a t-shirt. So I think you're convinced that this formula is going in the way that we're trying to get. This simple, universal, and beautiful formula. And how we can, for example, find the Higgs boson. I just demonstrated Higgs boson is really important, but how can we hunt it using an experiment? So the way we get this kind of information, this kind of new particles, is just by creating them. And the way we created them is using quantum physics. We know from quantum physics that we can transform energy into mass, provided that this transformation is following the conservation of energy. So we know mass is a kind of energy, mass is a type of energy, and since we can change one type of energy into the other, we can also transform mass into energy and energy into mass. And this is how we work. We give particles kinetic energy, this energy of something just for the fact that it's moving. So we make the particles turn at high speed so that they have high kinetic energy, and we make this energy to appear into mass by a collision. So the collision is just a transformation of kinetic energy into mass. And what kind of mass? All the different states of mass that are able to be produced in nature. So we're now in a really cold, stable universe in which we're living in. And the particles that are massive, that are really unstable because they are massive, they are not present in our environment. And the only way we can study them is just by creating them in a laboratory. So we can create this table that is hidden from our eyes because we're living in a stable universe, just constructed with these particles here. So the rest has been, the only way to study them is just by creating in a collision. So we make particles to accelerate and collide, and we put a detector that is able to study all the particles that arrive after the collision. So to understand a little more about the collision, let's make a small game so that you can see what is happening in the quantum world. In a normal world, if two cars are going ahead of each other, what we expect is that if they crashed, the parts of the car appear, right? So we'll have tire over there, have steering wheel over there, have the glasses, and this will happen in a normal situation, right? Or will be common sense for us. Quantum physics is not common sense, so forget about this and start thinking about this. A collision in a quantum world would look like this thing here. So it wouldn't be surprising for me that after two cars colliding, I would get a penguin. This is what happens in a quantum world. And this is something that is happening every day in our collisions. So out of a collision of two particles, wherever could appear, that is conserving energy first, and then it's consistent with nature. So everything that can happen is following this representation here. Conservation of energy is really important, and this is why this hunt of the Higgs boson has taken more than 40 years, because it's a really massive particle that can only be produced if your kinetic energy is consistent with the energy of this mass. So you need high energy collision to create high mass states, and that's why it took more than 40 years to find something similar to the Higgs boson. So these are the collisions that we're producing. So we have proton heading up on another proton, so it's a combination of course, and the bomb will produce particles that are not part of the initial protons. So for example, this would be a case, electron, muon, photon, photon. This could be a final state of a collision of two protons, this could be another one, this could be another one, this could be another one, and this would be the best situation, in which out of the collision we have something that we haven't seen before, and this would be a new particle. So we're trying to gather collisions, study collisions, and we're expecting that in some of these collisions something will happen, and this will be new physics that we'll have to study. Here is the Higgs boson, and what I want to remark here is the fact that we have to see a lot of collisions, because the probability of having a new collision, a new phenomenon happening is really, really small. It's in the order of 1 out of 10 to the 14. So we have to wait for a long time till we get a collision that is interesting in terms of physics. So now you understand why we have 10,000 people, why we spend some 1,000 million euros, and why we have this project here that is called the LHC, the Large Hadron Collider, that is this 27 kilometers long accelerator that is placed in near the city of Geneva, 100 meters underground. So we have this big tunnel, 27 kilometers long, that is providing conditions to understand better the laws of nature, as I said before, to dig down into the laws of nature for this understanding, just human curiosity about the universe. And this project, the CERN laboratory, has been working for more than 50 years and giving a lot of new surprise about the universe and nature. We have discovered different things, like for example the Higgs bosons were discovered at CERN, with more than, I think we have 5 Nobel Prizes working at this moment for CERN in one of the 20 different projects that we're running right now. So here you see the European members of CERN. The only members that are working at CERN are European countries. You see that we are more than 10,000 people working in 20 experiments with more than 60 countries working for that. And half of the particle physicists in the world are working directly or indirectly for this project. I think these numbers are quite impressive. As this map here, the shows not only the member states in blue, but also countries that are collaborating in this project, so that you can get an idea of how international is this project, and a big collaboration that is representative of international collaboration between different countries. And this is part of the project. This will be one of the dipoles that is making the particle turn. I will explain how it works in the day because it goes out of the topic of the presentation. But you can imagine in the end it's just like, I will try to summarize it in a few words. We have a battery that is accelerating particles, and we have magnets that are making the particle turn to get again to the battery that is accelerating, turning, accelerating, turning. So the challenges are the battery and the magnets that are making the particle turn in vacuum. We use these superconducting magnets. They are at 2 Kelvin degrees, that means less than 290 degrees Celsius, running this in parallel into 2 vacuum tubes that is made of these dipoles, 1,232 dipoles that are creating this 27 kilometers long accelerator running underground. So things like, for example, this is the biggest cryogenic system in the world. This is, if you ask me where is the coldest and emptiest place in the world, I will point to this experiment in the world, I mean in the universe. So there's impressive numbers. And behind this impressive number, you can guess this impressive technology and impressive challenges. And these challenges are somehow triggering new developments in things like, for example, superconductivity, vacuum, electronics, engineering. So these is things that are going to the society and directly from this kind of projects. So you accelerate particles, as I said before, you made them collide in one of the 4 experiments. The experiments are huge experiments of several thousand of tons. This one is 15,000 tons and of impressive size. This will be some 40 meters long, 30 meters high. So you can imagine this is 100 meters underground. It's an amazing project of 3,000 people each. So impressive collaborations working on the understanding of the collisions. And this will be another image of the project itself and the detector. This will be the detector I've been working for, and this will be the point where the particles are colliding and the different detectors and channels that are detecting these particles. Now from this image you can imagine the amount of electronic channels that we have to reconstruct the collision and to see the particles that are going up the collision. This will be a real picture of the detector when it was under contraction, let's say some 4 or 5 years ago. And here, one of the collisions. This is a real collision. So you see here the particles that are going out of the collision. These are the charged particles. And here again, energy deposits in different subdetectors that are in the final detector. The thing is that producing a collision in the LHC is really difficult. And to have a Higgs boson, if you're colliding one proton each second, you have to wait for thousands and thousands of years. So the solution creates a new challenge. The solution is based in increasing the frequency of the collisions. So we're colliding 40 million times per second. This is the collision rate of our protons. And we're not colliding one proton against one proton. We're colliding 10 to the 11 protons against 10 to the 11 protons in bunches separated by 7 meters and a number of 1,000 bunches. So we're creating collisions in an immense quantity every second. These collisions that are happening, as I said before, 40 million times per second, 10 to 11 protons against 10 to 11 protons, you can imagine the amount of information that is creating. And now you can guess somehow all the communication system that is behind this challenge.
The processing also.
Everything, relating with processing, storage, and in short, communication. So this is the link between what we're doing there and the communication world that we're trying to explore in this business week, right? So this is the number of information that we're creating. 300 gigabytes per second. So, challenge accepted. This is what the engineer said when this project was proposed. And they were kind of optimistic. And they were really optimistic because they learned from the past that these challenges are able to be successful in the end, and they're having something useful in return. So whenever you have a problem, you solve it, and you create something new. And this something new can make benefits to the humankind for the society. So they say, challenge accepted, we're going to do this. We're going to handle 300 gigabytes per second, because we know we can do it, and we know that this is the way to make a best world for human beings. I said that they learn from the past. This is the past. I present you LED accelerator. It was working at CERN in the same tunnel, so 27 kilometers long accelerator that was starting running in 1988 and stopped running in 2001. For these 20 years, they achieved many discoveries and many interesting things that were interesting for the physics of the present. They tried to find the Higgs boson. They were not successful because they didn't reach the energy that they needed. But this LED was an electron-positron collider that was successfully running from that time. It was the biggest and most powerful experiment by that period. And this is a picture of that. So the tunnel was starting to be constructed in 1983. Short after, 5 years after, the experiments were ready to start. And in 1989, it was clear that for such a big experiment, such an important project, something new should appear to handle all these new problems that can be appearing in such a big collaboration that this project needed. So in 1989, Tim Berners-Lee was a physicist at CERN. He was worried about information, how information was treated in such a big project, and how may communicate so many physicists to learn each other and send information between each other. So he released this proposal to the management of CERN. I repeated, this was 1989, and this is the chart that will explain how this project will work to exchange information. This is the original proposal, and I've been underlining the most important parts of this proposal, and let me read a little bit what is written here. So he was worried about the losing information at CERN. He observed that CERN was a really dynamical environment in which many physicists were arriving, many physicists were leaving, and many things are changing every second. When we're working with new technologies, you can find a new solution to something, and the other day you have a better solution, and dynamically you have to change one and the other, but this guy that discovered left, and this information can be lost. It is not a big problem. In the end, you try to get all the information and you solve the problem, but you are duplicating efforts. So it's really important to keep track of all the information that is appearing in such a project. And this is what he was worried about. How we can handle all this information so that it can be optimally distributed, and the people that are interested in can reach this information in a simple way. In this document, in this proposal, he arrived to this conclusion that a book to track all this information would be impractical. So he thought that something new was necessary. Probably this is the most important part of the document, in which he says something that I think is still it can be still applied to the present situation. CERN is somehow a replica of the universe in a small world, and it's a little bit advanced in the sense that the requirements that we have there will be the requirements of the society in the future. So what we're doing here to solve our problems will be the problems of the future. That is what it said here. The personal information nodes may be particularly accurate at CERN, but in this case, CERN is a model miniature of the rest of the world in a few years' time. CERN meets now some problems which the rest of the world will have to face soon. In 10 years, there may be many commercial solutions to the problems above, while today we need something to allow us to continue. These are the words of Tim Berners-Lee in 1989. And with these words here, backed by signing at the top of the proposal, these are the words from the supervisor of Tim Berners-Lee, a new era started, the era of internet. This is a communication. This era started that day, in 1989. So this is a good example of how these kind of projects can help society, and how there is a link between technology, society, and physics. This would be the proposal of Tim Berners-Lee. He created the web browser. This is the first web browser. The first internet web page from this World Wide Web was this one, info.cern.ch, and it was running a Next computer that is now shown at CERN like a monument. This was in 1989, and things changed rapidly. As you know, this part of the story we all searched, so we know what happened then. In 1990, they realized that not everybody can have a Next computer at home, so they created a web-based that was running any PC. So it started to be a public domain, and anybody could access this web. It was in 1991 when this was created, and soon after it's starting to spread all over the world. So in 1992 there were 26 servers in the world. 1993 more than 200 servers, and now you know how things have been exponentially increasing during the years, and how internet has become something that we are now considering necessary in our lives. So this is the story. This is the story of how a challenge that is accepted is is solved, and is interesting for the society and for the people. So we go to the present situation again. So this was just a little bit from the past, so that we can see and learn from the history. And now the situation again, 300 gigabytes per second. This is a new situation for society. Nobody found such a challenge before, and this is creating new opportunities. As I said before, I probably convinced you that this probably could be not only interesting for CERN, but since it's a miniature of the future society, it could be interesting for everybody. And I will explain how CERN solves this solution, and what will be the perspective for the future society based on the solution that CERN found for this problem. So this 300 gigabytes per second was solved by CERN in two ways. So first online, what is called trigger, and second offline, what is called grid. I will say a few words about trigger. It's not that interesting because it's not probably linked with communication, but I will stop at grid. A few words about trigger. It's just an online system that is able to reject or accept a collision in real time. So we get all this information from the event, and in real time we have to say if this event is interesting or not based on physics. So we have physical parameters that are saying if the event is potentially interesting or not. And we have to decide either if it's interesting or not on real time. We have a rejection rate of we get 1 out of 1 million. So it's an important reduction that is making our system to work at a slow rate. Let's say that this 300 gigabytes per second is possible to handle with present computers. So the first solution is just removing information. We know that all the information is not interesting. We know that the Higgs Bossom is appearing with a rate of 1 out of 10 to the 14. So we can just remove information without losing the interesting things. We're just removing what we think is not containing new physics. And this is what we call trigger. So with the trigger we have changed the problem of 300 gigabytes per second to some 300 megabytes per second. That is now something that is considered big, but still can be treated by what we call grid. So grid is the solution to this new problem of 300 megabytes per second, and the solution of grid is based on these two things. So on one side we have a possibility of one single laboratory to handle this amount of information. 300 megabytes per second is still a lot. And then we have another fact, is that CERN parent has access to national computing facilities. So we can get to these two pieces of information to get the solution. So why not, since CERN is not alone able to solve the problem, why don't we take all the big centers and we work out the solution just by integrating different facilities. So GRID is an integration of different facilities around the world to make all the system working at the rate necessary of these 300 megabytes per second. So I just copied there some words about grid that I found really interesting and describe perfectly how it works and the solution to the problem. So grid takes its name from the power grid, so now you can imagine how it works. It's the user transparently go to the network, and the network provides the solution to the user transparently in the sense that it's using all the facilities, but the final user is just taking the information from the grid. The Bayesian grid is then illimited. It's just integration of different laboratories. You can get as many laboratories as you want, and you make the system to be as power as you want. And so that you have one vast computing resource. You ask the information to the grid solves the problem with all the computers in the world and gives you the solution back. So basically what you're doing is sharing not only storage capabilities, but also competing resources. So if you are willing to have long computation, instead of doing it in your own PC, you send it to a PC probably in Nebraska, probably in UK. You never know where your job is running, but there is for sure a big center computing your information with a large storage capability and sending the answer back to you so that you can get it in a short time compared with the time it will take in a normal computer. And the final sentence that I think is the most important one: the grid may be part of people's daily lives in a decade. So learning from the past, one day grid will be not only application for CERN, but for normal uses. Today we can say that CERN, the grid that appeared like a CERN requirement for LHC, is now being used for astronomers. There are biologists working with ADN and proteins using grid, and we have many other different researchers using this kind of technologies to solve problems of computation that would be impossible to be treated with a normal computer. So instead of going to a supercomputer, you go to a grid. The problem to big computation that we have in science happening really often. And if we center the problem, the solution to the CERN case, so the LHC, this is the solution to the problem. This is what is grid for LHC. We have a hierarchical structure in which information is shared between different laboratories in 3 levels. 4 levels if we take into account the last one. So we have a tier 0, that is the peak of this pyramid, and this CERN. This is the biggest center, and it accounts to 20% of the final network. So 20% of storage and computing capabilities are at CERN. That will be the tier 1 here. This is where the information is reconstructed and primarily stored, and then sent to the different tier 1. We have 11 tier 1s. One is in fact in Spain, and these are spread all over the world. These 11 tier 1 work as a big centers, interchanging all this information coming from the tier 1, from the tier 0. Then we have the tier 1, tier 2. We have more than 140 facilities, laboratories in the world that are belonging to this network and are part of this tier 2. The information is coming from different tiers, so that the information is shared among all of them, and the user will just connect to the grid. The information will be found within the grid. The information will be treated one of these supercenters, this farm computer, and the information the solution to your ask will go back to the user transparently, just treated by the grid in this way. So this will be like a representation of the solutions. You have the experiment, and you have how the information can be treated depending on your information at tier 0, tier 2, or whatever it is. So the information is dynamically global dynamic system that is treating the information in an optimal way. This will be a map of different tiers in the world. So you can go to that application, and this dynamical. You can choose what are the centers. You see the distribution all over the world. We have South America, North America, Europe, and in Asia. So this is a global network you can see here. And you have there a Google Earth application in which you see not only the centers but also the links. You see how the information is sent from one center to the other, and with this application you can see a little bit more about the grid in LHC. So just coming to the end of this presentation, I just wanted to let you know about this presentation I did in September of the past year, 2012, and you can access it on YouTube in case you want more information. There you can get more detailed physical view about the problem. There I don't say any word about communication or internet, just collisions, Higgs boson, and physics. And finally, if you want to learn more about the association, I give you here the Twitter, the Facebook, and the webpage of the association that is really committed with the science and the spread of information related with science and especially at CERN. So conclusions of this talk are summarized here. So fundamental physics research is triggering technology in different areas. I showed you before electronics, superconductivity, vacuum. They are creating patents impressive rate, and also in communication, of course. The a good example of communication development is a World Wide Web that was designed at CERN as well for the lab project, and will be somehow, as I explained to you, a good motivation to think that grid could be one day a feature of communication. So this is the new challenge for LHC, and I hope it will be the future for our society, probably for us in 20 years or so. And that's it. So thank you very much.